Good morning, everyone. We're going to be starting very shortly with introductory remarks from Al Petronero. You will, as you come into the lobby, notice that you're on mute. That is by design. We have, as you can tell, over 140 participants at this point, with a few more to join. So just sit tight. We'll be underway in just a moment. Thank you.
Bonjour à tous, nous allons commencer sous peu. Comme vous pouvez le voir, quand vous vous joignez à la réunion, vous êtes automatiquement mis en sourdine. Nous sommes déjà plus de 140 participants, alors c'est juste pour s'assurer de ne pas trop avoir de son de fond. Alors nous allons commencer très bientôt avec une introduction de Alain Pietroniro et merci encore d'être ici avec nous aujourd'hui.
Okay, Evan, I think in order to stay on time here, I'll just start quickly, and then you can go through some of the sort of meeting logistics, and then we'll hand the floor over to Dave Harper and John Pomeroy. So, is that okay?
Yes, absolutely. Please do start. Thank you.
So, as people are getting on, I just want to say thank you to everybody for joining us this morning. This is the second annual Canadian Flood Forecasting Forum that we've pulled together. The first one was in Vancouver in 2019, pre-COVID times, if you can remember what that was like. And it was really a Canadian-focused meeting at the time. Those of you who don't maybe know the context, there was a renewal of the National Hydrological Service in Canada that came about in 2018, and part of that renewal was to look at a national flood guidance system developed through the Meteorological Service of Canada. I should mention, those of you who don't know me, I'm the former executive director of the National Hydrological Service for Canada. I recently retired and moved on to an academic career at the University of Calgary, where I'm a professor and chair in water resources and climate change. So we started organizing this meeting previous to retirement, and so I'm happy to continue collaborating with ECC on this and get through this meeting and move things forward for Canada. So so as I said, this is the first meeting since February 2019. And quite a lot has changed since our first meeting, and so we hope to get people caught up on what's going on, and certainly focus the 3 days from an international perspective down to a more Canadian perspective, even down to a regional perspective. And we're very excited about what we know will be some excellent talks. We've tied this in with with our ECC and NOAA agreement. There's a NOAA agreement between both countries with a focus on hydrological forecasting. So we're happy to have our NOAA colleagues here as well. And of course, we're happy to have our European colleagues here as well, because as we all know, flood guidance and flood forecasting is becoming an international effort at the moment. And so we want to make sure that Canada's tied in with that international effort. So that's the motivation behind the meeting. So again, thank you everybody for coming. I think we'll have probably close to 200 participants at the end of everybody getting in, and I suspect people will be coming in and out depending on their interest, but welcome to everybody. And maybe Evan, you can just go over the logistics quickly, and then we'll pass the floor to Dave Harper, who's the Director General of the monitoring group in the Meteorological Service of Canada, and to John Pomeroy, who's the Executive Director of the Global Water Futures Program. So, Evan.
Thank you, Al. Good morning. My name is Evan Friesenhan. I'm the Manager of Engineering Services West and North in the National Hydrological Service with Environment and Climate Change Canada. Again, echoing Al's comments, welcome. So, a few quick reminders. So, as you've noticed, as you come in, you're automatically muted. That is by design. For those who are presenting, you have been provided presenter status. When it is your time to present, please do unmute yourself and share your screen. After your presentation, if you haven't already, please send that presentation to me. For those who have questions, there will be spaces after the presentations for just a couple questions. All you have to do is raise your hand, clicking on that hand symbol on the top right corner. You'll be identified, and either the chair or the moderator will identify you. Unfortunately, with the Teams platform, a simultaneous translation is unavailable. However, for those people who do have questions, please do either use the chat or again raise your hand. And if you wish to ask your question in French, please do so, and we will have someone translate for you to the presenter if required. All right, that is everything I have. Al, so I'll pass it over to Al. Thank you.
Yeah, thanks, Evan. Alors, si vous avez des questions en français, s'il vous plaît, vous pouvez les mentionner en français, puis on va traduire. Alors, on s'excuse, mais c'était impossible d'avoir la translation commune avec le système Teams. Alors, on fait qu'est-ce qu'on peut avec pour nos collègues francophones. Okay, so we'll pass it on to Dave and John. So Dave, if you'd like to start, please, and just provide some introductory remarks on behalf of Environment and Climate Change Canada, that would be great.
Okay, super. Bienvenue tout le monde. Welcome to the second annual Flood Forecasting Forum. My name is Dave Harper. As Al mentioned, I'm the Director General of Monitoring and Data Services within the Meteorological Service of Canada. My team is responsible for leading the collection and management of meteorological, climatological, hydrometric, and environmental in support of water, weather, and climate services. So in addition to our atmospheric program, which collects data from our national upper air stations, our surface and marine weather and climate stations, our satellite receiving stations, and our lightning and radar networks, we also run the National Hydrological Service, which collects, manages, and shares quantity data, both water level and flow data through the National Hydrometric Network. It's important to note that while Canada's hydrometric network is operated by the National Hydrological Service, it's jointly administered through a collaborative cost-shared partnership with the provinces and territories. It's been in place for over 30 years. So on behalf of the provinces and territories, the NHS operates approximately 2,200 of the 2,800 water monitoring stations on rivers and lakes across Canada, and consolidates the water quantity data to provide an integrated view of the country's surface water resources. And of course, this data is essential to support water management decision-making in Canada. The NHS does other things, of course. It also provides engineering advice to Canada's domestic water boards, where water management implicates more than one province or territory. We also provide advice and support to Canada-US interjurisdictional water management through the International Joint Commission, and we support the global water agenda led through the World Meteorological Organization. And while we recognize that in Canada flood forecasting is the responsibility of provinces and territories, we're very much intent on supporting the provinces and territories on delivering their mandate. This means leveraging the federal government's data, supercomputer, and predictive capabilities to improve national flood forecasting and facilitating the necessary collaboration with partners both domestically and internationally to improve public safety of Canadians. Climate change, of course, is increasing the frequency and severity of floods globally. Floods cause more than $40 billion in damage worldwide annually. Insurance losses from flooding alone in Canada have been estimated at $1.8 billion between 2009 and 2017. And in the period of from 1970 to 2012, storms and floods have resulted in over 1 million deaths. Recognizing the socioeconomic implications of climate change and its associated impacts on water, the World Meteorological Organization decided to give greater priority to strengthening operational hydrological services and to improve monitoring and forecasting. The WMO has since promulgated 8 long-term ambitions that can help guide our collective hydrological services moving forward. These are that no one is surprised by a flood, everyone is prepared for a drought, hydroclimate and meteorological data support the food security agenda, high quality data supports science, science provides a sound basis for operational hydrology, we have a thorough knowledge of water resources of our world. Sustainable development is supported by information covering the full hydrological cycle, and water quality is known. The Government of Canada, as I'll refer to, their $90 million investment in the National Hydrological Service in 2018 reflects these ambitions and the current climate change crisis. Through this investment, we are rebuilding the NHS's engineering and technical capacity. We're addressing infrastructure rust out by repairing and replacing measurement structures. We're identifying new technologies to enhance monitoring, including increasing efficiencies in data production and information management, modernizing flow measurements and estimation methodologies, improving products and services, and developing standards. We are also developing our capabilities to predict water quantity in 5 of Canada's major water basins: the Great Lakes St. Lawrence River Basin, the Saskatchewan Nelson River Basin, the Mackenzie River Basin, and the Columbia and Churchill Basins. And as we move towards an Earth system modeling approach based on the coupling of atmospheric, oceanic, sea ice, land, hydrological, and socioeconomic models, we hope to develop forecasts and scenarios for minutes to seasonal, annual, decadal, and longer-term timescales. Of note as well, the Government of Canada is exploring the creation of a new Canada Water Agency to work together with provinces, territories, Indigenous communities, local authorities, scientists, and others to find the best ways to keep our water safe, clean, and well managed. With all this in mind, the forum will provide us with the chance to examine what some of our partners are doing with respect to flood forecasting and introduce our provincial and territorial partners to the larger global framework. It will offer an opportunity to examine some of the challenges and issues in Canada and to give all participants a sense of what is happening across the country and to open a discussion on data and model sharing between jurisdictions. We'll discuss the current state-of-the-art details regarding ECCC's or the MSC's development efforts in its national prediction system. And we'll examine some of the challenges and issues at the provincial and territorial levels across Canada and update each other on recent advances with a view to develop a community of practice and improve our collective approach to flood. As we mentioned, we wanted to bring a global perspective to this meeting and learn what others are doing around the world and how we can potentially work together. With that, we're very thankful to have NOAA here to provide their perspectives. NOAA is developing its next generation national forecasting system. So this presents us with a real opportunity to learn and exchange information. We also, of course, have a formal MOU, as Al mentioned, to support with NOAA to support Canada's transboundary obligations. And in this vein, we're very happy to have the International Joint Commission here as well, as they're key to facilitating transboundary water management between Canada and the US. I'll mention too, we'll be fortunate to hear from Florian Papenberger from the European Centre for Medium Range Weather Forecasts on some of their strategic hydrological directions. And also want to thank Global Water Futures and John Pomeroy, with whom we've had a long-standing partnership, and they've greatly assisted in putting this forum together. And finally, a big thanks to all the organizers, Prabin Rokaya, Chris DeBeer, and John from Global Water Futures, Dan Prince, Brendan Disher, Francois Zoku, Jacob Bruxer, Charmaine Herenque, Matthew Noteboom and Sheila Ball from the NHS, and a very special thanks to Al Petronero and very special thanks to Evan Friesenhan, who's managed to bring all this together. So with that, I look forward to all the presentations and some stimulating discussion, and we'll turn it over to Mr. Pomeroy to provide some additional remarks.
Well, thank you so much, David. And yeah, those are great remarks, and you covered the thank yous wonderfully well. I'd like to echo that, and also note that within Global Water Futures, the core modeling team has worked hard, and we'll hear from Martin Clark, and Pravin Roy has also helped us pull together many of our contributions. We're delighted to be here, and just honored to be here. It was almost 2 years ago, we had the first National Flood Forecasting Workshop in Canada, and the first time that we sat down of all 13 provinces and territories, and the federal government and the university sector and other partners came in and discussed our problems and our needs and how we might be able to work together better to solve these on a national basis. And that was an incredibly powerful meeting and really set the agenda that we're sitting on right now. And now today we have our US colleagues and European colleagues in there. We're looking at the transboundary basins with the US in much greater detail here. And there have been tremendous developments from the United States government with the National Water Center and NOAA's flood inundation mapping. So there are lots of things going on that we can tie into. From Global Water Futures, things have also developed since we met 2 years ago as well. We're still focused on our 3 key areas of delivering new capability for providing disaster warning, diagnosing and predicting change to water futures, and developing new models, tools, and approaches to manage water-related risks. And this has allowed us to develop a very strong relationship with Environment and Climate Change Canada, from observations to modeling to process understanding to science research, and we really appreciate that partnership. But we've also developed linkages with 478 partners across Canada. By linkages, this means at least a formal exchange of letters and probably more in-kind and direct support for the program, and that has allowed us to really reach out and link to our provincial government colleagues, to industry, to NGOs, to communities, to First Nations, and sectoral groups across the country. Global Water Futures now comprises 64 projects and core teams, one of which is our core modeling team, and it's one of the largest of these entities. It involves 18 universities across Canada, 190 funded university professors, and they've gone on to hire over 970 graduate students, postdocs, researchers, engineers, technicians, and others to drive the program forward. So it's probably the largest university-led water program in the world, and certainly the largest that we've ever seen in Canada. We've linked ourselves into 4 global programs to frame our work, and of course you'll hear a lot about the modeling work within Canada, but we're also you'll hear mention of a planetary water prediction initiative where we're trying to take some of our modeling internationally, and that's couched under the World Climate Research Program. We're the only GWEX regional hydroclimate project in North America and one of 3 in the world. We link in strongly to the World Meteorological Organization through its hydrology and cryosphere efforts, and have led a focus on high mountain predictions and observations. And then through UNESCO's International Hydrological Program and Future Earth's Water Sustainability Initiative. So a strong framing internationally to help us on those linkages as well. Here, what we're so excited about the announcement of the Canada Water Agency and the potential for greater federal investment and leadership on water, and but really the idea of a national approach that we've got the quarterback in there, but we have all the provinces and the territories and the industries and the communities and other sectors in there, so we can have a truly national flood and drought forecasting system, and then get imaginative and think about how do we bring water quality into this. How do we link it to helping reservoir managers manage water resources across the country, irrigation, scheduling, so many other things. So there's lots to do. You'll hear a lot about some of the contributions that Global Water Futures scientists are making over the course of the meeting, and we're here to help, and delighted to be working with you. And so thank you so much, and let's carry on.
Okay, great. Thank you, David and John, for those great remarks. We'll start off right away. I'd ask people who have their cameras on to turn them off if they're not speaking. It'll help with some of the bandwidth. And I'd ask the speakers to if they can choose to either be on camera or not. That's their oh, there's Tom, great. And so yeah, I'd like to introduce the first speaker, Tom Graziano, and I don't know if he'll be sharing it with Ed Clark, but they're from the National Weather Service in the US, and we're really excited to hear what's going on south of the border in terms of forecasting. Tom and I go way back to WMO and other initiatives, so welcome, Tom, and we'll start with his talk right away to set us off on the overview of NOAA's flood inundation mapping program and the whole National Water Center overview. So thanks, Tom, the floor is yours.
Thanks, Al, welcome everybody. Good morning or good afternoon, depending upon where you are. And Al, congratulations on your recent retirement. All right, I think Lauren is going to pull up my slides here. And there we go. And Ed couldn't be with us this morning. I'm the director of the Office of Water Prediction within the National Weather Service. And Ed is our deputy director of the Office of Water Prediction, also the director of the National Water Center. So I'll be speaking about the Water Center as part of my remarks this morning and sharing with you where we are with the facility and what it's enabled and where we plan to go from both a research and operations perspective. Next slide, please. So here's my outline for this morning. I'll talk a little bit about our Weather Service strategic vision and plan for the agency. I'll talk a little bit about the Water Center, our new national water model, which is essentially leading a bit of a transformation, if you will, of our water resources prediction and capabilities and related services. As you mentioned, Al, I will discuss where we are with regard to bringing real-time flood forecast and inundation mapping to bear operationally, and then say a few words about our Hydrologic Ensemble forecast service, which we use to provide risk-based stream flow information, which supports water supply, really all time range applications, but a big supporter of water supply applications in the United States. And then I'll summarize. Next slide, please. Okay, those of you familiar with the National Weather Service and NOAA, and you've heard our director, Dr. Louis Uccellini speak, you'll hear him speak to the strategic outcome of our agency, and that is about building a weather-ready nation. I know from a WMO perspective, this has been extended to a concept of weather-ready nations, and so there's an effort afoot in the WMO to expand this strategic outcome in that regard. And fundamentally, it's just developing or enabling society to be prepared for and responsive to weather, water, and climate-dependent events. And it's about building community resiliency in the face of increasing vulnerability to extreme weather, water, and climate events. And what we like to say in the United States anyway is we simply can't do it alone. We work very closely across the weather, water, climate enterprise with our partners, whether they be federal, state, local, private, academic, to build, deploy, support the capabilities that we leverage to provide the services that we provide. Next slide, please. The Office of Water Prediction, which I'm specifically the director of, this is our vision and mission. We envision a nation strengthened by timely and actionable information, right, to inform the decisions that folks need to make across the water resources stakeholder spectrum, whether it be, emergency management, water supply, navigation, recreation, agriculture, you name it, ecosystem management, all sorts of very diverse user group, and in some cases dealing with competing demands in various basins. So we're trying to provide the most timely, accurate, actionable information to inform those types of decisions so that we can leverage our limited water resources to the best of our ability and support those decisions. Our mission is to collaboratively research and develop, these capabilities. We do that. Our infrastructure within the Weather Service is, for those of you who aren't aware, We have one national center, that's the National Water Center. We have 13 regional river forecast centers, 12 in the continental United States, and then one that's located in Anchorage, Alaska. And then we have 122 weather forecast offices, which are in neighborhoods or communities across the United States, and they build, develop, foster relationships with our stakeholders at the community scale and state scale to provide the information needed to inform the decisions that need to be made. So we are about bringing the best tools, technology, science to bear operationally to support those decisions, and then we provide operational support through the National Water Center for, events that span multiple regions or multiple river domains of river forecast centers, as well as support our national partners in terms of their information data needs. Next slide, please. So where does it all start? For the last 20 years, frankly, we've been working with our stakeholder community across the United States, conducting all kinds of outreach across many fora. And fundamentally, when we have integrated, distilled, prioritized, what we've heard from our stakeholder community, and fundamentally asked our stakeholders, what keeps you up at night? What are the decisions that you make for which you currently have insufficient information, or you need better information, or a more complete picture of what the water resources situation is? And when we distilled all that information, conducted all those fora, and we continue to reach out to our stakeholders, it is a continuous process and very important aspect of what we do. But this is what these are the thematic areas that emerged: floods, droughts, water availability, water quality, and then of course climate change and the impact of climate change, on water quality, water availability, drought, and flooding. And what we heard from our stakeholders is that they need information at significantly higher fidelity than we've historically provided it. I think many of you who are familiar with our operation in the United States, we work hand in glove with the United States Geological Survey and the Army Corps of Engineers, the Bureau of Reclamation on a routine basis. But the USGS has about 8,200 stream gauges across the country. We routinely provide about our official river forecast born from our 13 river forecast centers at about daily forecasts at about 4,000 of those sites. What we have heard, while that's very important and usable information, we heard from our stakeholders is they want information at higher space-time scale, and they want information which expands beyond stream flow and stage, which really defines more, helps them understand better the full hydrologic budget within a particular basin. They want us to provide not only this higher fidelity information, but then help them as they integrate that information with other geospatial information to basically take it down to the street level and make that information actionable. So that's fundamentally the target that we've put on the wall for ourselves, or I should say our stakeholders have put on the wall for us. And that's what we're aiming at with the transformation that we're in the midst of. Next slide, please. Our strategic plan for the National Weather Service, if you were to look at it, it's a fairly high-level document, updated in 2019. There are 4 elements therein in section 1.8 of the document that refer to water specifically, and these are they. Delivering actionable water resources, as I mentioned, from the national to street level and across all timescales. Minutes to months river forecasts that quantify both atmospheric and hydrologic uncertainty. I mentioned earlier, I talked about the Hydrologic Ensemble Forecast Service, or HEFS, supporting our water management activities in this country and supporting forecast-informed reservoir operations. Improving forecasts of total water in the coastal zone. So we are in the process now of linking our operational forecast guidance for freshwater with our sister agencies, our National Ocean Services, coastal estuary modeling capabilities to generate routinely total water forecasts in the coastal zone. And this is particularly important, not only from a routine basis, but certainly when you have a landfalling hurricane or a nor'easter type storm and you've got you need to account, or we need to account for the combined effects of not only the freshwater, but the tide surge and wave action, and when predicting total water levels, and then the associated inundation. And then fourth and finally here, delivering forecasts of flood inundation linked with other geospatial information. This is a requirement that was articulated by the emergency management community in this country roughly about 20 years ago, in the wake of, in 1999, in the wake of Hurricanes Dennis and Floyd, when we saw large sections of South and North Carolina underwater. And we have been working toward this capability, and with the advent of the new national water model, which I will speak to at a high level, and Trey Flowers, the director of our analysis and prediction division, will speak to after the lunch break, is really a catalyst for this transformation that I've referred to, bringing information down to the street level at much higher time frequency. Next slide, please. Okay, the National Water Center. It's a new facility. I'll still use the word new. We cut the ribbon on this facility on the 26th of May, 2015. It is located on the campus of the University of Alabama in Tuscaloosa. It is a LEED Gold facility with a maximum occupancy of around 200 folks. We currently have about 105 people occupying the facility, although in our COVID situation, most of our folks are currently on a mandatory telework status still. It is designed to be a center for collaboration, one for excellence for water resource and science and prediction. We host an annual Innovators Program, or Summer Institute, in collaboration with our National Science Foundation and a group called Quasi. And for those of you who aren't familiar with Quasi, they are the consortium of universities for the advancement of hydrologic sciences, incorporated over 120 member institutions. And when we cut the ribbon on the facility back in May 26th of 2015, less than a week later, we held our first Summer Institute. And what we do at the Summer Institute, it's essentially a 7-week in residence program where we bring in graduate students from various universities around the country to focus on various themes that we have each summer. Those themes range from the national water model itself, preparing it for deployment and implementation, flood inundation mapping for multiple years. There's usually a social science element every year. We've looked at groundwater, terrain and bathymetry issues, dissemination issues, all sorts of things to accelerate our capabilities operationally and build a community of practice, at least in this country, around these areas of focus and expertise. Another thing that within our operations center, a goal is to build a water resources common operating picture for decision support services across all timescales. And while it is a NOAA facility, we invite other U.S. federal agencies to occupy space in our facility and work hand in glove with our team at the National Water Center. Since we opened the doors in the facility, we've had USGS employees in our facility, and we'll soon have the first liaison from our Federal Emergency Management Agency once we open the doors again, after we return to some sense of normalcy after the COVID pandemic, or as we deal with the COVID pandemic. Within our operations center, I mentioned we cut the ribbon in 2015. We declared IOC, however, for our operations center on the 1st of October 2019. And what did it mean to declare IOC? What it meant is we had our first 13 folks in that facility, and we were providing 14/7 operations out of our national center. We are moving in earnest toward a full operating capability. We've received a congressional mandate to do so and achieve that with 48 staff and residents in the operations center to support 24/7 operations by the end of fiscal year 22. So roughly about a year and a half from now. Our center provides routine coordination and collaboration with its internal and external partners. And we monitor and assess conditions, and we also generate, provide, post-processed information, actionable information to inform decisions, and work very closely with our field infrastructure as a reach-back capability for all of them. And for the first time, actually in the history of the Weather Service, we will have a centralized backup capability. We've demonstrated it now fully at the National Water Center for all 13 of our regional river forecast centers. Next slide, please. I mentioned the National Water Model and Dr. Flowers will get into this in a bit more detail after the mid-event break. It's our first foray into high-performance computing for water resources prediction within NOAA. It's a model that is run hourly. We basically generate forecasts of flow and other parameters on the NHD Plus version 2 grid, which is basically on an hourly basis providing forecasts for 2.7 million stream segments. You can see in these diagrams here, in sort of the purple color, reddish purple color, that is the primary stream network that our river forecast centers routinely provide forecasts for. And then the higher spatial detail you can see in the inset on the right shows the additional level of detail. It's about a 700-fold increase in spatial density that the National Water Model rather, is now providing forecasts on an hourly basis. And next slide, please. Okay. One of the new capabilities that we're very excited about, as I mentioned, it's been a long-standing requirement articulated some 20 years ago by our emergency management community, is to provide real-time flood forecast inundation maps. The map on the left here basically shows about 200 locations at which we have leveraged hydrology and hydraulic analyses conducted by our Federal Emergency Management Agency, or FEMA, where they've generated regulatory flood insurance maps. We've leveraged that information and extended it to produce flood inundation map libraries, which only extend a relatively short distance up or downstream from a USGS stream gauge at those roughly 200 locations. What we are in the process of doing now is demonstrating the capability in real time, essentially for the majority of the continental United States, leveraging a capability called HAND, or height above nearest drainage. It's a model agnostic approach to generating a flood inundation map. We are continuing. We are basically providing in real time in an experimental basis for our 12 CONUS RFCs, or continental United States RFCs. We're able to put any out-of-bank condition that's forecast by a river forecast center. We're essentially able to map that, put it on a map, and we're also doing that with regard to the guidance output from the National Water Model, although we don't have complete coverage just yet for the entire country, although anticipate we'll be there by the end of this calendar year. And again, we're currently demonstrating it for that capability for about 120 million U.S. citizens, and of 100 of the 330 that reside in this country. Next slide, please. Okay, next slide is not showing up for me. I don't know if others of you. Oh, there we go. So this is basically the way we leverage and map the forecasts that come out of our river forecast centers. Is we use an approach called replace and route. We simply take the forecast that's made by a river forecast center at a USGS stream gauge location, and we essentially drop it into the stream network that's defined by the National Water Model, at least the main stems, and we'll route that water downstream. You can see for Hurricane Harvey, forecast inundation map, leveraging the replace and route approach. And then on the right, you can see for the same forecast and same valid time, the output from the National Water Model. they appear very similar in nature. And what you see with the National Water Model is filling in a lot of the gaps between the main stems and the tribs, so that, you know, providing information now from the National Water Model, whether it be a river forecast or a flood inundation map, in areas where essentially we provided none before. So this is about, you know, promoting service equity across this country and providing all citizens of this country equal access to the same information to support the decisions they need to make to protect life and property. Next slide, please. This effort within the Department of Commerce has received a lot of attention. In fact, both in 2018 and 19, it was identified as an agency priority goal, and the Department of Commerce is a very large agency. The Weather Service, NOAA are one small part of that, but this was one of a handful of agency priority goals that that they have asked us to pursue. We did that in 2018 and 19 for the domain of the West Gulf River Forecast Center, and are doing it again for 2020 and 21 for the domain of the Northeast River Forecast Center, and really expanding well beyond the domains of those two RFCs. As I mentioned, we anticipate by the end of this calendar year having experimental guidance available for all 12 CONUS River Forecast Centers. And what do we drive that with? Well, we drive it again with the forecast from the River Forecast Centers, as well as the National Water Model forecast flows. We utilize from the National Water Model, both the analysis cycle, the current conditions, a short range forecast out through 18 hours driven by that's forced by the HER model, or the high resolution rapid refresh model, which cycles hourly, and then the medium range forecast out to 10 days, which we provide output on a 6-hourly basis out through 10 days. Next slide, please. And I realize I don't have much time left, so I'll try to conclude here soon. I mentioned the Hydrologic Ensemble Forecast Service. This is our minutes to months to year, essentially, forecast capability that is deployed by our river forecast centers, supported certainly by the National Water Center and the Office of Water Prediction from a science and technology perspective and an implementation perspective, seamlessly providing probabilistic or risk-based information from an hour out to a year, accounts for both the uncertainty both in the atmospheric forecasts as well as the hydrologic model. These are outputs which are consistent across space and time. We drive that with the best available atmospheric forcings that we have. In this case, we leverage heavily the Global Ensemble Forecast Service, or System rather, or GEFS, which was recently updated, and I'll show you how that was updated on the next slide. And these are used. There's many applications of the HEFS output, but increasingly being used to support what we call forecast-informed reservoir operations. So trying to optimize the use, improve those inflow forecasts into major reservoirs, and optimize the use of what water resources we have for a whole host of applications. Sometimes particularly important when they're competing in nature. Next slide, please. A bit more about our HEFS implementation status. Right now, we've got it deployed at 1,390 river locations. We completed baseline validation at 1,828 river forecast locations, and by December of 2022, we plan to fully implement this capability at all 3,400 locations across the country, which are the official river forecast, which are a subset of the official river forecast points that the 13 river forecast centers, regional river forecast centers, routinely provide river forecasts. One enhancement that just occurred is we're in the process of transitioning from forcing the HEFS with the GEFS V10 with the GEFS V12. GEFS V12 was implemented in September of this past year. It expands, you can see the number of ensemble members, extends the forecast out to 35 days for the 00Z cycle, and utilizing anew the FD3 finite volume Q-sphere dynamical core, and with a substantial increase in horizontal resolution. Next slide, please. I believe this is my last. Yes. So, in summary, we're advancing our water science and services, and it continues to be a big priority for NOAA and the National Weather Service. I also serve as the chair of NOAA's water team, and I'm responsible for leading the integration and coordination of water-related activities across all of NOAA. And Ed serves on the NOAA water team with me. We support, as I mentioned, the modeling done by our river forecast centers through the FUSE and CHIPS platforms, and we'll hear a little bit more about that later today with some real-world examples from David Valley, who is our hydrologist in charge at our Northeast River Forecast Center. And you'll also hear from Dr. Fred Ogden, our chief scientist, on how we're evolving the National Water Model. What do we see as the next generation of the National Water Model? I think you'll find that particularly interesting. The National Water Center, as I mentioned, is a center of excellence and catalyst for collaboration. And we're continuing to develop and evolve our hydrologic modeling capabilities for a very broad spectrum of stakeholders whose needs continue to increase. So with that, I will conclude, Al, turn it back your way. I don't know if there's time for questions or not, but you let me know. Thanks.
Great. Thanks a lot, Tom. That was a great overview. We really appreciate that. It's nice to see all the efforts in the US going on and moving all those yardsticks forward. So we probably have time for one quick question. We started 10 minutes later because of logistics and stuff. So the way it works is you put your hand up, it's supposed to go to the top of the page and we should see it. So if anybody has a quick question, that'd be great. If not, we can move on. Oh, Martin Clark and Rob Phillips, and we'll stop there. So 2 questions. Martin first.
Yeah, hi Tom. That was a nice presentation. Thanks.
Hi, Martin.
Yeah, I was really pleased to see the focus on ensemble prediction capabilities. Can you talk a little bit about some of the development efforts that you have there as to what's new in the research phase?
Sure. With regard to ensemble prediction, I think I think you might know we're working with our colleagues out in Boulder from an atmospheric forcing perspective to improve the forcings both that drive our hydrologic ensemble forecast service, but also look at strategies, pending sufficient HPC resources to generate the National Water Model guidance and an ensemble, provide ensemble predictions through the National Water Model and extend the range of those predictions. Right now we do what we call sort of a poor man's ensemble, if you will. We do a time-lagged ensemble with the medium range version of the model to try to characterize, at least in some way, shape, or form, the uncertainty in those medium range forecasts. But that is an area of particular interest on our part. There's another effort ongoing in the US where we are looking to generate the optimal blend of all of the atmospheric guidance that's available. It's called the National Blend of Models. And so one of the things that we're exploring is looking at this optimal blend and then generating, probability density functions that then could drive an ensemble variant of the medium range version of the model to capture the uncertainty, at least through that range as a starter for us moving forward. So those are some of the areas that we're particularly interested in and areas where we certainly need additional focus. So thanks.
Okay, great. Thanks, Tom. Rob, if it's a quick question, please, that'd be great. And we can move on to get the next speaker lined up. Thanks.
Yes, it's related, Tom, to your mention of merging water quality in that type of monitoring with the hydraulic models and everything else. What do you see as the key challenges in doing so? Thank you.
Yeah, sure. So from a water quality perspective, and first of all, that's something that sort of an aspirational goal of ours that we have. It's something, our sister agency, the National Marine Fisheries Service, is the only regulatory part of NOAA and they very much need water quality information as a starter. Just water temperature information would greatly help inform the kinds of decisions that they need to make. We recognize we need to go farther than that. The current model architecture, if you will, the WRF Hydro architecture that we're utilizing with the first generation of the National Water Model doesn't lend itself easily to the integration of some of these new capabilities. Hence, the Water Model Next Gen, which Fred Ogden will speak to later, which is an open source, much more flexible architecture is what we're building with some of our sister federal agencies to much more rapidly integrate and accelerate development of those types of capabilities. So we recognize that needs to be done. It's a bit of a tall order with the current architecture we have. So we are moving in earnest to re-architect the model as you know it, to enable those capabilities to be brought to bear operationally. So thanks.
Great, thanks for the question, Robert, and thanks, Tom. That was great, and I'm sure we'll be taking furious notes on the Canadian side to see how we can try to emulate some of the great work being done on south of the border. So thank you. So Florian, we'll get you lined up for the next talk, please. So Florian is the Director of Forecast at Ecmwf. I believe hydrologist by training, Florian, if that's correct. And look forward to your talk. Thank you. Are you trying to speak, Florian? Because you're still on mute.
No, I'm trying to speak. I should be unmuted. You thought after 1 year I could learn that one. Maybe not. So I'm Florian Pappenberger, Director of Forecasts at the European Weather Center. And as rightly pointed out, I'm actually a hydrologist by background. And usually I have to give this presentation the other way around, where I have to sort of explain to meteorologists why hydrology is actually quite important. So this time it's the other way around. Within the remit of my job, I'm now responsible for all forecasts at Ecmwf, and I'm going to show you a small fraction of that. What I'm actually trying to do is trying to get you to get interested into two documents which I just put into the chat. One of them is the new strategy, which we just published, and the other one is actually a sort of derived discussion document, and that doesn't entirely only focus on hydrology, but more on natural hazards. Just for those who don't know us, very quickly, we're an international organization based in Reading, UK, Bologna, Italy, and Bonn, Germany. And we are operating mainly medium-range monthly and seasonal forecasts, founded really to create weather forecasts on that range. To do that, just a little bit of background, because I think it's also very important later for hydrology. The thing we're already doing nowadays is actually we're getting about 800 million daily observations. And these 800 million daily observations are used to drive our weather forecasts, but not just the weather forecasts, also, as you can see, some elements here in terms of ocean, but also in terms of hydrology. Unfortunately, only hydrological measurement on that one here is probably soil moisture. I apologize for that. What do we do with that? We produce mainly medium-range weather forecasts. With medium range, I mean forecasts for the globe from 3 to 15 days. We also have monthly forecasts, which are going out to 46 days. And then we have seasonal forecasts, which go out of the region. So that's our main NWB forecast ranges. On top of that, we're working very closely with the European Union. One of our goals is to provide environmental information on top of the weather forecast, and I've just listed here 4 of the main sectors which we operate in. One is atmospheric monitoring, so that's water quality forecasts, and you may have seen some recent publications about Saharan sand dust moving over the oceans. Climate change is a big element for us. For that, we produce the Reanalysis, which I believe some of you have used, so a past state of the atmosphere in the Earth system, but also a multi-model seasonal forecast, which I'm pleased to say also includes the Canadian seasonal forecasting system, as well as about 6 different other national forecasting systems. On top of that, we're producing something called a flood forecast. We're producing a global version of the flood forecast, and I put the websites underneath, and I put the websites only for that underneath because I know you're all hydrologists, so you may be most interested in that. and also a finer resolution European version, which produces forecasts every day up to 15 days. And then last but not least, slightly linked to hydrology, fire forecasting, which is also produced on a global and European scale and sort of produces a fire risk index, different versions. One of them is actually the Canadian, or the index developed in Canada, which is the fire weather index. All these data are available for downloading. They're part of a climate data store, and here I've only listed the data which are available for the hydrology, and you can see you can download those data. In the bottom right is the link if you want to look for it. However, what I'm really here to is today, and I'm going to do this very briefly to be fair, is to show you our new strategy. I said usually I have to sort of explain it the other way around, but we've just developed a new strategy. We do this every 5 years, and we set ourselves new goals, and we refresh old goals, and the mission is really still to deliver global medium-range numerical weather predictions and monitoring of the Earth system, mainly to our member states, which you see as green. But of course, our forecasting systems are global and therefore available everywhere. And we're really trying to do this through cutting-edge science and in collaboration with everybody across the globe in that sense. This is going to be a long lead up to where I'm actually want to get to. It's sort of linked into 3 pillars and 6 goals. Strategies always have to have some pillars and goals, I feel. Anyway, you can see in there there's impact, science and technology, but also organization and people. Of course, hydrological science and hydrological forecasting sits in the science and technology one, which you see world-leading Earth system science. It sits also in the computing aspects, and I don't know how much we're going to hear about this in this conference, but it has become more computational challenges to produce high-resolution forecasts. And then, of course, most importantly, it sits in the impact section, in particular in producing forecasts and products fit for purpose. I've sort of spelled this strategy out, and I don't really want you to read all of that. It's sort of trying to subdivide those 6 different goals, and just to sort of trying to, does it not work? No, it doesn't. Great. Sort of trying to find where water plays an important role. One of them is actually that in the future we would like to aim more in producing an Earth system forecast in which we have a more realistic
Is everybody frozen? Is it just me?
I'm frozen here.
Yeah.
Yeah, frozen here.
Agreed.
Okay. Yeah, it looks like something happened. Let's give it a minute and we'll see.
in order to get better to the temperature forecasts, in a very rough sense. My majority colleagues will probably now crucify me for that comment, but I think it's also true. Then, this is not going well, I'm so sorry. Just to catch up a bit of time, I think in order to do that, I'm going to talk a little bit quickly about a digital twin and explain to you why it has to do with hydrology. But last but not least, there's of course 2 other resolution data, so high resolution information, it becomes actually quite difficult for anybody to use that type of information. So Ecmwf is part of weather forecasting system, but in order to actually advance into the future, we need a full Earth system model. Earth system, of course, here is meant in a far wider sense than just hydrology. It does mean what you saw on the left-hand side, a record-breaking year for tropical cyclones. We ran out of letters ran out of names this time, as most of you know. It means really getting new satellites on course and using them, but it does mean what I mentioned before, a fully closed water cycle in the monitoring and the forecasting to really be able to do a future Earth system. If you break that down for many of my colleagues, it tends to mean what I'm showing here, a sort of set of equations. And I have to say this slide always makes me extremely cringe, because I know that many of the things which are on this slide, we can't actually neither measure on the scale I need them, nor do we have really an idea how they're physically 100% related on the scales I'm talking about, maybe on many other scales too. But what we're really trying to do at Ecmwf is sort of trying to go back in terms of connecting these type of energy and water budgets also in developing our forecast system. So rather than saying we're going to do the best 2-meter temperature forecast, we also now want to know what's circled in here. What is the runoff? How well do we represent runoff? With all, of course, this difficulty of trying to measure or determine that. Just one thing which is actually not very visible in my slides, I noticed, all of that is always set within the concept of uncertainties. I thoroughly believe that a single deterministic forecast is worthless, particularly on the timescales I'm interested in. You may be surprised that one of the first things we actually have to do is add rivers. We are running a massively huge Earth system, and the Earth system has no rivers in it. It has disconnected sails. So what we're currently doing is actually something very simplistic. What you've seen sort of in the previous slides is just adding rivers to transport water from a grid cell or from a point into the sea. Sounds very simplistic. So far at Ecmwf, in terms of producing forecasts, we didn't really think about this. We didn't need this because we didn't need to work on a water closure of the balance or the air system. Secondly, we're looking at how to optimize hydrology. Each forecasting system has an Earth system attached to it. We have a massive land surface models. Ours is called H-Tesla at the moment. It has been there for a very, very long time and has been developed further and further. It was always part of the forecasting system. However, it didn't really lend itself to be optimized and used in a hydrologic concept. So on top of adding something like simple as a river, we also now need to rethink how do we actually work with our land surface scheme to be really part of the atmospheric modeling system. For that, it becomes really simple. We have to do things like refactoring the entire code. We have to think, how do we optimize and use parameters about different scales? Ecmwf currently runs about 5 different types of resolution. So you run an ensemble system at roughly 18 kilometer, a high resolution system at 9 kilometer, a reanalysis at 28 kilometer, and a seasonal forecast at a lower resolution even. So we're running different forecasting system resolutions, and we need to make sure that the parameters and the functions between those different resolutions do actually make sense and are fit together. So far in the past, we have been less worried about this. Last but not least, something which is actually quite traditionally done in hydrology, but also in meteorology, we need to work out how we actually assign parameters and how we actually estimate parameters in that forecasting system. This has been done by tuning quite traditionally in meteorology already for a long time, and sort of those methods of tuning have been applied to the land surface scheme. We know that the two disciplines have slightly different attitude to calibration and parameter estimation. Here we're sort of trying to bring the hydrological concepts of parameter estimation into the land surface scheme and then hopefully extend it further in the boundary layers. So one element which I sort of don't want to neglect is that if you have a strategy about an Earth system modeling, and if you are an operational forecasting system, it's not just about the science. It's actually how do you get this science into an operational forecasting chain. And we heard how difficult it is actually to move from a building where you cut the ribbon into a forecasting framework or forecasting readiness framework. That's a huge and tremendous effort which really has to be appreciated and applauded. It's not easily to be done. So in order to actually go the next step, we have to make sure that the land surface becomes an intrinsic part of a forecasting system. That sort of is the current status where we're moving to and where we're moving to in our strategy. We really have set ourselves now a different goal too. And these are 2 pictures which I think are quite striking. On the left-hand side, you've got an NASA Apollo mission taken in 1969. On the right-hand side, you actually have a model. This model is the current Ecmwf model, uses some old reanalysis data on a 28 kilometer resolution. And you can actually see it starts becoming look alike a little bit. If I would go back, you would very often see very coarse resolutions of that. So that wouldn't be working. What does this mean? This means that we're now aiming to produce what we call a digital twin. Digital twin is a fairly common theme or topic outside, in the outside and other types of settings. And it's really for us to become even higher resolution. Our current highest resolution forecasting system is, as I said, 9 kilometer globally. We're now aiming for 1 to 5 kilometer. For that, we really need to rethink this. We need to rethink how we do model this, how we do represent this. What does hydrology mean on a 1 kilometer global scale? How do we represent uncertainties on a 1 kilometer scale? How do we actually get that thing running on a 1 kilometer scale? So this is our next goal. It's called a digital twin of the Earth. Just to show you some very initial examples, and I sort of have to apologize because it's more showing pretty pictures than actually showing results which are sort of tensioned against verification data. One of them is the current attempt for us to produce an offline surface model which allows running in 1 kilometer, and you sort of see what this means. It has all sorts of challenges on a global scale. Land use and land cover being one of the big ones, but also how do you represent coastal areas and lakes on that resolution? We have issues with snow over orography and orography underneath that. We have issues in how to represent catchment hydrology in an adequate sense in a global model whilst being on that high resolution. How do we improve skin temperature for data assimilation is one of the points I mentioned here too. So it's just the beginning of a journey. It's the beginning of a journey of actually trying to get somewhere in order to produce this global forecasts. Performance is a big issue for us. We need to issue a forecast when it's still useful to the user. So we, of course, have to get the forecast running in a quick enough time. So that's sort of a sidearm here. That's why I sort of said about technology and science and computer science, which plays a more important role. What we also do on top of that is actually trying to improve the global flood forecast and the European flood forecast. So we're going to move to 1 arc-minute resolution for the European window and a 3 arc-minute resolution for the rest of the globe. And what you see here is actually 1 arc-minute river network over Europe. So it's not the 3 arc-minute. Sorry, I couldn't find the picture for North America quick enough to show you that one. But it's sort of our next step in getting closer to this high resolution. These are the first exploratory areas that we want to move to. So apart from bringing hydrology into the meteorological forecast, the other aim we have now is to actually improve the hydrology itself significantly. That sort of takes us slightly, of course, to a third aim which we are having is actually making our forecast more important for impacts. And we're working on new ways of trying to get an impact or risk matrix into this global and global forecasting system as well as in the European forecasting system. And if you log onto the websites of the global forecasting systems or globalfloods.eu, you already find some of those simplified risk matrices. Currently, they're mainly based on inundation forecasts globally and then connected to the population affected. So not very sophisticated yet. But we're trying to move from a pure forecast of a hydrology now into the forecast of the impact as well. So I tried to make up some time and just to give you a summary. So we're really moving towards a global Earth system model. That means a closed water budget. I'm not so sure it's going to happen in 10 years, but we can at least give it a good go in an operational Earth system model. So not just an offline version. We need to reduce bias in hydrological relevant variables. We have massive problems with snowmelt, for example, which we hope to address slowly. And we need to produce more physically realistic hydrological variables, which is de facto just me admitting that sometimes what Ecmwf produces in its Earth system in terms of hydrology wouldn't really stand the scrutiny of hydrologists looking at it. For that, we're going to go and work on a concept called the digital twin for high resolution modeling of extreme events. I didn't so much talk about extreme events. That's more in the paper which I posted. And really, the other element is on the digital twin to work on data assimilation and hydrological applications. I haven't really talked much about data assimilation and hydrological applications. That's a big area for operational forecasting where we not really have moved on a lot. We have moved on in assimilating hydrological variables for the benefit of the weather forecast and, as mentioned before, something like 2 meter temperature. but we have sort of still quite a big gap in terms of research and working on operational data simulation. As I said, we're trying to aim for multi-impact risk assessment, which hopefully gives us a better tool for decision making. Above all, we're trying to make data access easier and easier. We're actually trying to encourage the uptake of data and work throughout the new collaborations. The element which I left out completely in this talk is actually our strategy is also quite heavy on AI and machine learning, but that's a talk I'm going to give on Thursday on a slightly different slant on the types and strategy. Thank you very much for joining, and thank you very much for listening. And I'm going to repost the links, and I hope I'm not frozen anymore.
You're good, Florian.
Lucky me.
Yeah, so thanks, Florian. That was great. We'll get everybody on mute. Feedback. So a couple of take homes. I think it's great. I think we're kind of in a new paradigm. I think both Tom and Florian showed quite clearly that there's a convergence between hydrology and meteorology right now, and we're trying to figure it all out. So it's interesting times for sure. And the enterprise is going global. I mean, we can see that quite clearly from both these talks that we are moving into a kind of a global paradigm here. So I think it's great for the provinces and territories, particularly to sort of get caught up on some of this if they're not already, and to learn from what we're doing here and see how we want to move Canada forward in this context, right? Because we'll be working with Ecmwf and with NOAA down the road for sure, and it's good to know what others are doing. So appreciate that, Florian. Any quick questions for Florian? I don't see any hands. Okay, great. Well, thanks again, Florian. So we'll go to our next speaker. So now we'll bring it to the Canadian context. As we mentioned, Canada's just at the sort of beginning stages of developing its national law.
Okay, great. Thank you, and I'll try to make up for 5 minutes. We're late about 5 minutes right now. The previous talk was very interesting, so thank you, Florian, for that. A very interesting vision. Here I'm going to present the systems that we are currently implementing, so it's a rather more technical talk. It's an update on the development of our national flow forecasting guidance system. There's a whole team that worked on this presentation. I'll just mention my colleague Dorothy Durnford at the Canadian Centre for Meteorological and Environmental Prediction. Do you see my slides?
Not yet.
Okay. Now, how's that?
Wait, perfect, thank you.
Good. Okay, so I work at the Canadian Meteorological Centre, although I haven't been there in a year. So this is a building that hosts 3 major organizations in the same building. So the Meteorological Research Division, this is where I work. The Canadian Centre for Meteorological and Environmental Prediction, which is part of the Meteorological Service of Canada, and Shared Services Canada that deal with the supercomputer infrastructure. So we have in the same building research, development, IT support, and operations, and coffee. And this integration into a single building has really helped over the years. We've managed to work virtually for a year, but we're eager to go back to this building. Our mandate there is to predict and inform all Canadians of changes in the atmosphere and of potential high impact situations or events for Canadians and the environment. CMC operates numerical weather and environmental prediction models for that purpose. They're real-time, 24/7. They promote warning preparedness and adaptation to the risks posed by changes in the natural environment. There are a few freshwater prediction systems or related to freshwater at CMC. We have analysis and reanalysis systems. The most known is the Canadian Precipitation Analysis, which is a QPE that's been in operation since 2011. We now have a reanalysis system of surface variables and precipitation. So this will be a 40+ year reanalysis. 18 years are already available, so I'll be talking about that. Then we have the National Surface and River Prediction System, also known as GEMHydro, and internally as Nsrps. So this is a Canada-wide high-resolution offline prediction system for the surface, lakes, reservoirs, and rivers. It provides 6-day forecasts, deterministic right now. We're aiming for operational status in 2022, and a 32-day ensemble forecast, which should be operational a year later. We also operate the water cycle prediction system, which is a two-way coupled atmospheric surface, river, large lakes, and ocean prediction system. It provides 3.5-day deterministic forecast for the Great Lakes, from the Great Lakes to the Gulf of St. Lawrence. And actually it includes part of the Atlantic Ocean. It's fully operational, but it uses a land surface model, but it is less advanced than that of the Nsrps, which is SVS. So this is our this system is really focused on closing the water budget at the regional scale. Then we also have an operational hydrodynamic prediction system called SHOP, based on the H2D2 hydrodynamic model, which provides 2-day deterministic forecasts for the St. Lawrence River. And here we're talking both about flows and levels. And Ensemble forecasting version is under development. In my talk, I will be focusing on the first two systems. So the analysis and reanalysis systems and the Nsrps. You'll hear more about the other two in Dorothy's presentation this afternoon. This is really a collaborative RDO effort between academia, providing and proposing and testing ideas for improving models, as well as analysis and forecasting systems, training HQP, the Meteorological Research Division, performing research and development, proposing new and improved systems for operational implementation, then CCMEP, developing and maintaining the operational systems, delivering the analyses and forecasts in real time, and the National Hydrological Services, which provides quality-controlled data and information to stakeholders. The way innovations are implemented at CMC is currently through what is called innovation cycles. So most numerical prediction systems are updated at the same time through a process that's called an innovation cycle, and we're currently in innovation cycle 3. So you will be hearing about innovations. They will be implemented in 2021 as part of this innovation cycle 3. So it starts with years of research and development, then we assess which innovations are ready for implementation. Then final cycles are performed where we look at the combined impact of all selected innovations on past historical periods, and this is where we're at right now. Then we do parallel runs where the old and new versions are running in parallel for weeks or months, depending on the system. And then we go ahead with the operational implementation if all goes well. And we get information that feeds into the research and development for the next cycle. I just want to touch on the difference between operational versus experimental at CMC, because you'll hear about experimental systems, but they're actually very close to operational systems. So when you have new systems for which there is not an existing system in place to replace, they first get this experimental status so that we can look at them over a couple of months or years. They are operated as if they were fully operational, and products can be provided to users for evaluation and testing, and as well as an additional source of information for decision making. They are reliable, but 24/7 support is not guaranteed. To get the operational status, it requires stability, documentation, performance metrics and standards for upgrading the system, and 24/7 support is required. And then updates to an operational system requires a parallel run with the new and old systems running side by side. So currently, the CAPA system, the precipitation analysis, is fully operational. The RDRS, that's the Reanalysis, and the Nsrps or Gem Hydro are still experimental, but they could become fully operational as early as next year. I'll touch briefly on CAPA. We currently have two versions. One which covers all of North America at 10-kilometer resolution, and one which has a higher resolution, 2.5 kilometers, but focusing on Canada with the exception of the Arctic Islands, and also the northern half of the United States. So it's a quantitative precipitation estimate product. The difference between the two, so the 10-kilometer version has been operational for almost 10 years now, and it assimilates more information because we've started to assimilate satellite data in it, whereas the 2.5-kilometer version doesn't have the satellite data yet assimilated, but it has higher horizontal resolution. And it's been operational since March 2018. Recent developments as part of Innovation Cycle 3, we've started to assimilate additional in situ precipitation data sets. So this is an ongoing effort to assimilate provincial or co-op networks that are available in Canada or in the US. We're talking here about Manitoba Agriculture, the Toronto Region Conservation Authority, and the Grand River Conservation Authority. Both the last two are in Ontario. We're assimilating now additional S-band radars, satellite retrievals from the iMerge product in the 10-kilometer version, and we're contributing to a binational precipitation analysis. You'll hear more about this in Jim Knoll's talk later today. The new networks in Manitoba are this one. This is the Manitoba Agriculture, so quite a large number of stations in the southern half of Manitoba, and this is in the Toronto region. These are the additional radars, so we currently are assimilating the radars in blue, shown in blue, and we're adding the orange radars here in the US and the green ones in Canada. So we'll have better coverage. So you can see this is for the window, the 2.5 kilometer window. You can see that the northern half of the country is poorly covered by radar, which is why, in part, we've looked at assimilating satellite data. So this is, on the left, the iMerge early product based on microwave data that's calibrated using the GPM radar. And on the right is the impact it has on the threat score. So this is a measure of skill of the analysis as a function on the x-axis of the precipitation amount per year. I'm assuming it's per day because we produce 6-hour and 24-hour analyses. So I think this is for the 24-hour total. So in blue, you see the skill of the system without the assimilation of iMerge, and in red, it's width. iMerge has mostly an impact on the our summer skill because we only assimilate iMerge when we assess that liquid precipitation is occurring. The next system I want to talk about is the regional deterministic reanalysis system. So this is quite new, that the product's been available for the period of starting of the 21st century. I'm not sure if it's 2001 or 2000. I think it's 2000 to 2017 right now that's available. And it will be distributed through the CASPAR portal hosted by the University of Waterloo. So it's a 10-kilometer reanalysis with hourly outputs. And soon, I would say in April, we'll be going back to 1980 with it. So it actually uses an atmospheric reanalysis provided by Ecmwf, their older ERA interim analysis, which has an 80-kilometer resolution, and it's used only as initial conditions for the atmosphere for running our own global atmospheric model at 40-kilometer resolution, which is then dynamically downscaled to 10-kilometer resolution over North America. What's neat about this system is that there's two-way coupling with a land data assimilation system that improves surface conditions, so soil moisture and soil temperature and snow through an Ensemble Kalman filter. And this Ensemble Kalman filter actually makes use of the Canadian precipitation analysis as an input to get better precipitation forcing at the surface. And then this feeds back for the next run, providing improve the conditions at the surface. So this system is submitted. The system description has been submitted for publication in HES, Hydrology and Earth System Sciences, and we hope that it will be available in the coming weeks online. So yeah, the production is completed, should be completed by the end of March, and it's these years that are already completed, so 2000 to 2017. Samples are already used for multiple hydrological model intercomparison studies, including the GRIP-E, GRIP-GL, and Nelson MIP projects. So this is over Lake Erie, over the Great Lakes, and over the Nelson River. Here we're looking at maps of precipitation from, so this is the global GPCP product, fairly low resolution, but providing global coverage over both continental and ocean surfaces. The central panel is the NOAA Stage 4 MPE product, providing very detailed information over the US and some small parts of Canada, such as the Columbia River Basin. And that's our new reanalysis for precipitation at 10 kilometers, so slightly lower resolution than MPE, but higher than GPCP, and providing coverage over both continental and ocean surfaces as well. So we can see that there are lots of similarities between Stage 4 and CAPA over the US, which is normal, and some similarities with GPCP at large scale, but large differences as well if you look at Quebec, for example, where there's much more precipitation in CAPA, and it's probably due to the fact that we're assimilating more gauges, and in particular gauges from the Réseau Météorologique Coopératif du Québec. So the other system I want to talk to you about is the Nsrps, the National Surface and River Prediction System. So this is a picture that you'll see a couple of times over the next days. So it's okay if you don't master it all at once. Essentially, this is an offline surface and river prediction system that has two modes: an analysis mode on the left, where we figure out what are the current conditions of the surface and in the rivers, and a forecast mode where we essentially forecast into the future for days to up to 1 month, actually, in the Ensemble version. This slide is for the deterministic system that actually goes up to 6 days. So we have the top part is the surface prediction system, where we forecast, we analyze, we produce analysis and forecasts of surface variables such as soil moisture, snow, temperatures, and also fluxes such as runoff that then feed into the river prediction system. So the grid runoff feeds into the river prediction system that provide us with 1 kilometer estimates of flow for most of the country. Here are the domains covered by the land surface model and the routing model. Currently, the land surface model is run on this gray rectangle, so again covering most of Canada and the northern half of the US. And then we do the routing on selected watersheds, but that do go from all the way from the Yukon to Newfoundland. We are missing only a few of the major rivers in Canada that don't drain into the Arctic Basin or the Hudson Bay. And we're working on increasing coverage, for example, to cover the Saint Jean River. An Nsrps has a surface component that works from the weather forecast and does some downscaling to bring it to a higher resolution, and does this integration at higher resolution, 2.5 kilometer, for the whole forecast period, because it's less costly to run just the surface at a higher resolution. I'll give you an example. So here I'm illustrating the impact of downscaling for precipitation forcing. So this is a zoom on the Bow River watershed, where we're looking at assessing daily rain and snow totals for one day in 2013, where there was a lot of precipitation. So we're looking at the Kappa 10 kilometer product here on the top left for rain, and then snow on the top right, using a 3 degrees Celsius thresholds for differentiating between rain and snow here, just for illustration purposes. And then this is what the surface prediction system sees as input after it's downscaled to 1 kilometer based on topography. So you have more snow in the mountains and less rain. So much more detailed inputs into the surface prediction system. This is what it typically looks like at a 6-day forecast looks like for Canada. So top left, this is a total precipitation forecast for 6 days with lots of details due to this downscaling for precipitation here. Top right is soil moisture, top left temperature, surface temperature, and bottom right, so bottom left temperature and bottom right runoff. So I'll be just looking at a few regions. Here we have a zone with relatively little precipitation and low soil moisture as well, relatively high temperature. And this was a zone with forest fires at the time. Here is the impact of a hurricane that had landed at the time, with lots of precipitation, wet region, relatively relatively colder here, and then lots of runoff. Another hurricane that landed a few days later with lots of precipitation in the Maritimes, lots of soil moisture, and so fairly warm, and lots of runoff again. Here's another region where we're looking at precipitation, but the signal in soil moisture is not really wet, because this was actually snow. So so the temperatures were fairly low, but there was still snow melt leading to runoff. This is what the corresponding river forecast looks like. So at this scale, it's hard to distinguish anything. We're looking at flow forecast on a log scale. Zooming in, here we're zooming on Great Slave Lake. This is the Hay River, one of the main rivers flowing into Great Slave Lake with the Slave River. So this is the level of details we get at 1 kilometer for this large lake that is in the Northwest Territories. So on the right here, you see over the course of the summer of 2020, the one-day forecasts that were issued. So these were forecasts 24 hours out of hourly flows, in blue the observed flow, and in orange the actual forecast that was issued. So fairly good fit for that river. If we look at recent developments with the Nsrps, we've been working a lot on improving the assimilation systems. So the snow assimilation with the assimilation of the IMS satellite product, assimilation of soil moisture satellite information. We were already assimilating satellite information from the SMOS satellite. We're now adding SMAP, and Also, an improvement to the assimilation system is that we are now getting streamflow observations from USGS and provinces in addition to our own observations. So that leads to a major improvement in the Great Lakes region, for example. To the forecast system, we have made also improvements, looking at an improved representation of turbulent fluxes in stable conditions, and also very important, a new reservoir routing model to finally start representing a reservoir regulation instead of representing reservoirs as natural lakes. So I won't go into much details, but this is the IMS product that we're assimilating now for snow extent, and that actually improves the hydrological forecasts. This is a slide on the Dctr reservoir model that we are now including for many of the reservoirs in the model domain. You're looking here at Lake of the Woods on the right, outflow and storage over multiple years. In blue, the observed, in black, the observed. In blue, this is the simulation we got previously with our natural lake model, which assumed a stage discharge relationship. And then, so that's for outflow in the top plot. The bottom plot is for storage. So we have a major improvement for both outflow and storage at that location. Typically, we were doing a decent job for outflow, but not so much for storage. In this case, we improved both. And this is quite important that we do a good job for storage, because it then allows us to assimilate eventually water level information that could come from a satellite in the future for storage. The streamflow data assimilation in the routing model really has a major impact on the scale of the forecast. Even if we currently use a fairly simple nudging method with upstream propagation of corrections based on an area ratio method, it's really efficient at reducing errors for the first 2-3 days. But more sophisticated methods are being considered in order to update, in particular, the lower zone storage and assimilate satellite altimetry data. Here I'm showing for different subdomains the impact of upstream propagation of corrections on the standard error of forecast as function of lead time, so from 1 to 6 days on each plot for different subdomains. In blue, it's without the data assimilation, without this upstream propagation, and in red, it's the standard error with upstream propagation. So really, it has a major impact on the scale. This is going to be my last slide. We really want to have a tiered approach for hydrological products and services. Depending on the specific needs of the users, the information from the Nsrps can be obtained at various levels of the numerical modeling cascade. And the numerical guidance can be made available through either flat files or interactive web services. So we start by using the weather forecast from the atmospheric models. We downscale those forecasts to make them of better quality. We then perform precipitation and surface analysis and forecasts. This in turn gives us grid runoff analysis and forecasts that can be turned into stream flow, net basin supply, analysis and forecasts, and then into specialized products and services. That, in most cases, will be done by partners from the numerical guidance. So in order to deliver the products and services to end users, partners can hook up at different stages in the process and take over from there the production of flow forecasts. Thank you very much. I'll be taking questions if there are any.
Okay, thank you, Lisa. So that was a great talk. So hopefully our provincial and territorial partners sort of know where we're going in Canada with respect to our numerical guidance, and then hopefully we've updated our US and the European colleagues as well as sort of where we're at with respect to our flood guidance system in Canada. So we have time for a quick question. If anybody has one, please put your little hand up and we'll be able to answer. And I'll just point out there'll be lots of time for discussion, particularly with the provinces and territories in the next coming days as well around some of these issues as well. So. Okay, so thanks again, Vincent. We'll move on to the next speaker, please. So that's Martin Clark. Martin will give an overview of sort of what's going on with global water futures in terms of our core modeling effort and some of the research that's ongoing, and a lot of this ties into the operational system in ECCC, which is great. So Martin's a professor in Department of Geography at the University of Saskatchewan, and the core modeling lead with myself for the GWF core modeling team. So Martin, the floor is yours.
Okay, great. I assume you can see my slides?
Yes, perfect.
Yep. Okay, great. Thanks. So just to get into it, John introduced global water futures at the beginning. John's the director of global water futures. Main focus is the solutions to water threats in an era of global change. Focus on water science for cold regions and address the strategic needs of the Canadian economy and in terms of adapting to climate change and managing the risks of uncertain water futures. So huge application areas in global water futures are really streamflow forecasting and water security assessments. As Al mentioned, the Global Water Futures core modelling theme is led by himself and me. We're lucky to have Praveen Rakoya, who's the core modelling coordinator, who keeps many of us on track. We have a number of different research themes: spatial meteorological data, led by Julie Theroux; geospatial intelligence, led by me; current generation hydrological modelling, led by Bruce Davison; next generation hydrological modelling, led by John Pomeroy; water quality modelling, led by Philippe Van Capellen; water resources modelling, led by Tricia Stadnick; hydroeconomics, Roy Brower; and hydrological forecasting, led by Al Petronero. And all told, we've got about 31 faculty involved, 33 research personnel, primarily postdocs, and 21 collaborators. As John mentioned, associated with core modelling, we also have the Global Water Futures Planetary Water Prediction Initiative, and that's really to exploit the science advances that we're making in global water futures to improve our understanding and predictions of the global hydrological cycle. Some of the work that we're doing is building the computational infrastructure that we need to apply models across large geographical domains, but then really beginning to hone in specific subregions around the world where cold region hydrological processes are really important, and work with the people in those regions to improve the predictions that are possible. There's a lot going on, so today I'm not going to try to cover it all. I did want to give some highlights of some of the work that's going on for the spatial meteorological forcing data and geospatial intelligence and next generation hydrological modelling. I'm only going to touch on that briefly because John's going to talk about that in more detail immediately after lunch. Water resources modelling and hydrological forecasting. So for spatial meteorological forcing data, the forcing data sets that we have, they're used to correct biases in atmospheric models and used to drive hydrological models. So they underpin a lot of the work that we're doing. We've got three different thrusts in there. One is to improve the reanalysis data sets, retrospective analysis as to a hydrometeorological forcing that we have over the last few decades. Big focus there is on developing probabilistic forcing data sets, and I'll focus on that in the subsequent slides. New regional climate model simulations. So Julie Theroux is working a lot on GEM simulations across some of our key domains, and Yanping Liu is working on continental domain simulations with the WRF model with her colleagues at NCAR. There's also a lot of work on downscaling and bias correction. It's led by Simon Papalexio for CMIP6, and some additional work that Yanping is doing on bias correcting the WRF CONUS 2 datasets. So I just want to give some examples, give a flavor as to some of the work that's going on. Go-Chung Tang has recently published a serially complete data set for North America, providing serially complete data for about 30,000 stations across the continent. And the reason for this is that when we're interested in having stations as the backbone for our interpolation system to estimate the spatial meteorological forcing data set, we can do a lot better when we've got serially complete records. Also, having serially complete records can reduce some of the abrupt jumps that we have when stations are coming in and out of the data networks. So his approach has got a few steps to it: comprehensive quality control of data from the different networks, 16 different infilling and reconstruction strategies based on different forms of quantile mapping using Reanalysis estimates, machine learning methods, and multi-strategy merging methods. In this figure on the right here, I'm showing just some examples of the ratio of which methods are used when we're using these different infilling strategies that are shown in the different columns there. Some independent validation, correcting climatological biases, and comparing to additional benchmarking data sets. We've been using this as part of our effort to develop the Ensemble meteorological forcing data set for North America. So when we're getting into North America, the problems that we have are with the sparse station coverage in the northern latitudes. So what we're showing here is the number of stations within a specific search radius. So you can see on the left that search radio less than about 200 kilometers, we're often only getting one station, and you've got to go out for much larger search radiuses to get 20 stations or 30 stations. So a key part of what we're doing here for the Ensemble meteorological forcing data set for North America is optimal interpolation with a suite of different reanalysis products. This work builds on some previous work that we did with station-based estimates across the US. So Andy Newman published in 2015 our Ensemble data set across the contiguous United States. And then more recently, we've had Ensemble data sets for Hawaii, Ensemble data sets for Alaska, additional methodological advances that we had, in each of those. Some of it's, climatologically aided interpolation, representing precipitation undercatch, for the Alaska data set, etc. The main methodological innovation that we have for the Ensemble meteorological data set for North America, as I mentioned, is to combine the reanalysis data sets that we have. So on the left here, there's a number of steps. We're starting with the serially complete data set for North America. Our estimates are based on locally weighted linear logistic regression, and then we process the reanalysis data, ERA 5, MERA 2, GRA 55, using locally weighted regression to get that down to the spatial scales that we're interested in, optimally combine the station regression with the reanalysis station, and generate ensembles. I have a couple of figures here to show the skill that we have. This is maps of probability of precipitation at individual station locations, the probability of precipitation that we get from the ensemble, which is in the middle, and then the difference between the ensemble and the station. We look at probabilistic evaluation of this data, so we look at discrimination and reliability. So discrimination is effectively asking, to what extent are the PDFs different when we have events or non-events. There you're seeing the PDF of precipitation and the red where we've got an event, and when we don't have the event. The reliability is saying what's the fraction of time that an event occurs at different probability thresholds, and strongly reliable forecasts are on the 1-to-1 line. So what we're seeing is, in terms of our discrimination and reliability, it's quite reliable forecasts. The discriminations, what we see is similar to other data sets other probabilistic data sets that have been published. So the summary for that is that we've combined the station observations and the reanalysis outputs. We've got 100 ensemble members with daily precipitation amount, mean daily temperature, and the temperature range. We've got the data set available at 0.1 degree spatial resolution from 1979 to 2018, and that's available there. So as we're moving forward, the Ensemble meteorological data set for North America is we're going to be using to quantify the extent to which hydrological uncertainty stems from uncertainty in the meteorological forcing data that's used as input to the models. As we mentioned, we're working on the Planetary Water Prediction Initiative. So Gochang has extended his serially complete data set across North America to provide serially complete data for the planet. Then he's also been working on developing an ensemble meteorological forcing data set for the planet. This is in its early stages, its initial stages of development. What I'm showing in this figure here is the precipitation for the globe from era 5, just for 1 month, from January 1950. Precipitation from era 5 precipitation from the stations from that same month, and then some example ensemble members that we're generating using this method. Switch to the geospatial intelligence. What we see, and this is not unique, is on the presentations that have been given this morning, is that the hydrological models have got common requirements for DEM analysis, parameter inference, etc. But many of the models that we use different tools. So we're interested in developing new data sets and new model workflows to simplify the configuration aspects of hydrological models. We're interested in process-based parameter inference over large regions. Florian talked about that a lot with the MPR approach, the multi-scale parameter regionalization approach that he's applying with the HTESL model. There's other approaches that can be used for that as well, and we're looking at the advantages and limitations of those different approaches. And then developing a formal benchmarking system that includes multi-scale process-based model evaluation. This is work that Al Petronero is taking the lead on, looking at comparing model simulations with the data from research watersheds, providing a catalogue of past modelling efforts so that we understand and can quantify our model improvements versus the efforts that have gone on in the past, and integrating and synthesizing process understanding and data sets across different environments. What I want to focus on is the model configuration aspect, because this can be a big time sink, and there's lots of work that we can do to build a community of practice and really begin to share more effectively the tools and the methods that we're working on. What I'm showing on the right here is a paper that was published in Water Resources Research a few years ago, asking the question, if computational is not really reproducible, is it really science? And the point that a lot of computational hydrology, it was really difficult for people to look at the papers and reproduce what was done. So the work that Wouter Knerven is leading is to try to produce reproducible and shareable workflows to reduce the amount of time and effort that's required for the model configuration tasks. This makes it easier to keep track of the work for reporting and paper reviews, easier to collaborate, and large efficiency gains if we can do a better job of sharing code and concepts across different model development groups. The example that we've been taking has been to set up the SUMA model across North America and pull together the data that we need for topography, soil, vegetation, land use, forcing data, river networks, etc. When we look at this in terms of a workflow type system, we can see that there's a number of tasks that we may need to delineate the basins, process the digital elevation data, process the soils data, process the vegetation data, process the meteorological data, process the river network data, etc. And the details in here, you can read these if you're interested in. The details aren't necessarily that important. The main take-home message that I wanted to get from this slide is what's in the green at the bottom. Is that the green in the bottom is what could be specific to a specific model, and all of the tasks in the top are more model agnostic, and that they're required for any large domain hydrological model. So what Wouter's been doing is been trying to carefully separate out the model agnostic tasks from the model specific tasks, where the model agnostic tasks are in terms of specifying the domain and compiling the parameter data, the forcing data, the routing data. And then the model specific tasks are really just a thin layer, a thin interface that's responsible for taking the model agnostic workflow that's been developing and tailoring that for a specific model. So the goal there is really to improve the efficiency of continental domain model implementation tasks, as I said before, to make it easier to collaborate, to increase transparency, reproducibility, and code reuse. And this is really working towards the paradigm of advancing community hydrological modeling rather than a community hydrological model. So we see this with our colleagues in the US with their IHTM initiative. We see this in other parts of the world, and we're really interested in advancing the extent to which we can share some of our codes and concepts across different model development groups. We'll return to this later in the presentation as well. Next generation hydrological modelling. I'm looking forward to the talks after lunch by both Fred Ogden and John Pomeroy talking about this. I'm just going to touch on this briefly because John's going to be talking about this in more detail after lunch. The two main research foci that we have multi-scale, multi-physics modeling capabilities as the first foci, providing flexibility in how we represent processes, flexibility in our spatial configurations, having all dominant processes from headwaters to estuaries, canopy to bedrock, etc. A lot of work going on there that's pushing the boundaries, especially with respect to the snow modeling capabilities. And then the other foci is the hierarchical coupling workflow infrastructure, thinking about intra-component coupling, where we may add new capabilities to an existing model, inter-component coupling to manage exchange of information for different model components, multi-model coupling, where we may have a chain of discrete models, and workflow management to manage the flow of information that we'd have in complex forecasting systems. It's the work that Louise Arnaud is involved in and is going to be talking about tomorrow. So if we think about a hierarchical coupling strategy, this is an example of what's affectionately known as the Lollipop Diagram that we'd see in modelling institutes from NCAR. Actually, this is from NCAR, where we're thinking about an Earth system model where we've got a land, atmosphere, ocean, and sea ice component that exchanges information with a coupler. We can think of the land model as its own coupler, where in the land model we may have a glacier component, a biogeophysics component, a biogeochemistry component, river and lakes component, groundwater component, etc. And then in each of those components, we can have additional coupling strategy. So in addition to the flat coupling strategy that we see in a lot of existing model frameworks, we can see that we can couple model components at a wide range of different levels of model granularity. Key aspects of what we're doing that I think are important and potentially useful is that we have a combination of intercomponent and intra-component coupling. So we understand that some of the decisions that we're making are at a finer level of granularity and are better integrated in the code base of existing models rather than through more formal coupling methods. The second major advance is that we're including the numerical solution as an integral part of the coupler. So as we're going across, different elements of the terrestrial system, glacier biogeophysics, biogeochemistry, or even within the biogeophysics component, vegetation, snow, soil, etc. We often, have some type of operator splitting methods where we solve the equations independently, but we need to monitor the numerical error that we have that's a result of that splitting and control the numerical error so that we can have adaptive substepping in each element of the model system. So within the model component, this is an example of SUMA that we're beginning to integrate the next generation hydrological modelling capabilities, integrate in with some of the Canadian hydrological model capabilities that are being developed. As showed before, this is just one component of a larger complex system, but it's got its own hierarchical structure where we can look at the model architecture, selection and arrangement of the state variables, the model parameterizations, which may be the functions that we use to describe the relationship between the model states and fluxes and the model parameters. So the way that we've constructed a model like this is the first thing that we did is that we cleanly separated the model physics from the numerical solution, and that provides a really important aspect of modularity, and that allows us to take advantage of third-party solvers and capitalize on the advances that have been made in numerical methods over the last few decades. And a lot of existing land models and the state updates that we see are often sprinkled through the model like confetti at a wedding, and it can be very, very difficult to understand where the state updates are made and to begin to integrate additional modelling capabilities. I think Tom Graziano mentioned some of the problems with wharf hydro in that regard in terms of adding water quality aspects to the model. We have modularity at the level of model fluxes, which simplifies sharing code and concepts across different model development groups. And we've got the code structure, which is similar in many respects to BMI, which I know is being looked at by the National Water Centre now. Our code structure, we refactored that in order to integrate SUMA within the land information system from NASA with Krista Peters-Lagarde, and that's done to simplify integration with other model frameworks. So there's a lot there. There's a lot going on, but also a lot of opportunity to collaborate with other groups who are doing similar things. In terms of water resources modelling, the key aspect there, this is work that's being led by Trish Stadnick, is to represent the human impacts on the terrestrial water cycle across Canada. We're interested in applying water management benchmarks to compare the water management representation in Earth system models compared with more complicated integrated water resource models, and then also to advance water management in Earth system models, getting representation of small lakes, large lakes, managed lakes, water diversions and irrigation, etc. So a lot of our work has been on the Meteorological model, which is providing some of the computational horsepower for this. The Meteorological model takes HRU average runoff, routes it through the hill slopes, routes it through the river reaches to provide stream flow at different points in the river network. Part of our challenge recently, as we've been going to larger domain model instantiations, has been parallelizing hierarchical river networks. So for our river network decomposition, give the example of the Mississippi River Basin because it's one of the most challenging river basins in the world in terms of its large and hierarchical structure. So what we've done is we've had a threshold in terms of the number of upstream reaches that we use to disaggregate the domain into large basins, or decompose the domain spatially into large basins. So here's an example with 4 domains, 8 domains, 16 domains, etc. And then we've got 2 main criteria that we have, 2 main objectives. The first is that we try to balance the load across the processes, and then also we want to minimize communication costs across the processes. So here's an example here where we're zooming in to the 16 domains, where each of these larger tributaries and the color are handled separately across different processes. The smaller grey tributaries are handled by the main stem processor so that we can minimize the cost of communicating information from all of these smaller tributaries to the main stem. So we've got a 2-stage parallelization strategy. So here's the example, with the 4 domains here, where we've got processor 2 handling those 2 domains, processor 3, that 1 domain, processor 1, the red domain, and all of the smaller tributaries are handled by the master processor and the grey. So we have additional spatial decomposition using OpenMP for each of the subdomains, and then we have the bottleneck in the main stem, which is also parallelized by OpenMP, but the bottleneck that we have in the main stem is limiting the scaling capability that we have when we're running for individual river basins. This is what it looks like here as we're applying this globally. So this is an example of a decomposition into 36 domains. What we're showing here is the results for OpenMP and without OpenMP, in the blue and the red respectively. The dashed line is the perfect scaling. And as we go globally, when there's lots of river basins to work with, it's not a big parallelization challenge, and we can get very, very close to the perfect scaling. When we look at the Mississippi River Basin, this is an example here where we've decomposed it into 16 domains, showing again with OpenMP with 16 threads in the blue and without OpenMP, and the perfect scaling is the dotted lines here. We're getting deviations from perfect scaling, or large deviations from perfect scaling, because of the bottleneck that we have in the main stem. So that's something that we're still looking into in a little bit more detail. For lakes and reservoirs, we've done a lot of work to incorporate lakes and reservoirs into Meteorological. This is an example here of streamflow simulations for the Mackenzie River Basin, where you can see changes in lake level and the colours, for each of the large lakes. We've got some comparisons with observations. This is just early days yet, but we seem to be getting into the right ballpark. This is a lot of work that Siobhan Gahari is doing with Naoki Mizukami. In terms of the hydrological forecasting, I'm not going to be talking about this a lot because Louise Arnal has got a talk on this tomorrow. So this is the theme in core modelling that Al is leading, looking at comprehensive evaluation and advances in operational hydrological forecasting, with focus on system development, hydrological prediction development, and hydrological prediction test beds. The figure on the right is an example of the work from Vincent Vianney and Dorothy Durnford, done in collaboration between Environment Canada and Global Water Futures, especially with John Pomeroy, for simulations of the 2013 flood in Canmore. So you'll hear some of this tomorrow in Louisa's presentation. She's looking at different forecasting workflows, data-driven workflow to improve empirical seasonal streamflow forecasts across Canada, and then also a process-based workflow. So I'm not going to go into that in detail, just to say that a lot of this is beginning to tie together a lot of the prediction work that we have in the program, where we can see the work that we're doing in the initialization period, where we run the model up to the start of the forecast to estimate the initial hydrological states, where we've got to pull together our work on spatial interpolation of the meteorological forcing data, run that through our process-based hydrological models, work on snow data assimilation in order to produce our retrospective model simulations, and then have the best possible initial hydrological states that we're using for our forecasts into the future, where we've got spatial downscaling of our numerical weather prediction models to produce local scale meteorological forecasts, which are used as input to our process-based hydrological models to produce forecasts of stream flow. So I think we'll be returning to different aspects of this diagram over the next couple of days. So to sum up quickly, because I think I'm mostly out of time, our work in GWF core modeling has focused on developing the computational infrastructure to enable large domain hydrological modeling, focused on both deterministic and probabilistic forecasting capabilities. A lot of our work revolves around ensembles, especially providing ensembles of the spatial meteorological forcing data set, excuse me, and also characterizing the uncertainty that we have in the hydrological models itself. We have a model agnostic philosophy with focus on community hydrological modeling rather than developing a community model. And as I mentioned before, our main intent is to advance a community of practice to more effectively share code and concepts across different model development groups. There's a lot that we can share, and that's a huge focus of what we're doing. And more generally, we're interested in developing state-of-the-art capabilities in predicting terrestrial water, energy, and biogeochemical cycles, and I'm really looking forward to more collaborations. So I'll end it there and see if there's any questions. Thanks.
Great, thanks very much, Martin. So a quick question for Martin, anybody? Thanks for the overview, Martin. Okay, I don't see any hands up, so great. So that was a fantastic first morning. Really appreciate all the speakers, and thank you for getting us on time. That's wonderful. You know, if you do have any concerns or questions about this, you can always email Evan or myself, and we'll get back to you. I think a few people have emailed some questions, which we're happy to reach out to the folks giving talks to answer those questions. And at this point, it's time for the noon break, I guess, for those of you in Eastern Canada or Central Canada. And we'll try to be right on time. It's now 12:15 Eastern time, so let's reconvene at 1 o'clock Eastern and start with Trey Flowers' talk right away. And it looks like we have some really interesting talks this afternoon, and it continues on after coffee to some specifics around the transboundary and some of the products and services elements as well. So please, everybody, hopefully you can join up after lunch here. We'll meet up at the 1 o'clock Eastern right on time. We'll start right away, and look forward to this afternoon's conversation. So for now, Evan, I believe we're going to shut down. Is that correct, or are we going to leave it open?
We'll keep it open. However, if people want to log off and then log back in, they're more than welcome. Okay, well, for those of you in Ontario, Quebec, and Eastern Canada and Eastern US, enjoy your lunch. For those of you in Europe, go have a beer, I guess. And for those of us in the West, we'll have our coffee break. So thanks, everybody, and we'll see you very soon. Bye-bye.